This is Embedded Systems Design class, and we will continue discussing BIC24 modules. And today we will talk about timers and output compare modules. We will start with the timers. And in BIC24, we have two modes. We sometimes if we have an internal clock, we call it a timer. If we have an external clock, we call it a counter. These are the two modes. There is a general equation to calculate the time if you have a periodic clock, where time equals to the ticks multiplied by the clock period of the counter. In another way, if you change the mathematical formation for this side, you could say that the period is actually the reciprocal of the frequency. So it's going to be equal to the number of ticks divided by the frequency of the counter. And this is obvious. So if you want to calculate the total time of certain number of ticks, you see how much time does a single tick takes, which is the clock period of the counter, and then multiply it by the number of the ticks. Also, if you want to find the number of ticks, then you can do some simple mathematical manipulation, and you say that the ticks is equal to the time divided by the clock period of the counter. As an example, if you say you have a 16-bit timer and you have the frequency of the instructions is equal to 40 megahertz, or in another way, you would say that the frequency of oscillation is 80 megahertz, and you want to count from the minimum possible value, which is 0x0000, to the maximum possible value, which is 0xFFFF. Now, each one of them will be considered a single tick. So you have 2 to the power of 16, which is 56,536 ticks. And now you can calculate the time by applying this formula, and you would say that the time is equal to 56,536 divided by 40 mega, which will give you 1.6384 millisecond. And now this is the general idea about any timer in any microcontroller. For our BIC24 specific, we have specific equations. You are actually given a pre-scale value. This value will prolong the time for each tick. So now the time is equal to the ticks multiplied by the pre-scaled value divided by the frequency of the instruction cycle. It's actually the same as this one. We only added the pre-scale value in the numerator. So you have the ticks times the pre-scale value divided by the frequency of the instruction cycle. And from that, you can find also the ticks, and you would see that the ticks is equal to the time multiplied by the frequency of oscillation. Oh, sorry, for the frequency of the instruction cycle divided by the pre-scaled value. That's the first thing that a BIC24 timer have, a pre-scale value that you need to know about, and we will see it in details soon. And the other thing is the period register. The period register is actually a stopping point for you. So instead of counting from 000 all the way to the maximum, you could stop in somewhere in the middle by providing this number in the period register. So you have PRX, X being either 1 or 2 or 3, because we have only 3 timers in BIC24. It controls the amount of time for setting the timer interrupt flag, which controls the timer roll of time. So it tells you when the timer expires. And from this calculation, we would say now, instead of the time now, we will have the time for this flag to be fired. So the timer for, or the time for this timer interrupt flag is equal, instead of the ticks now, we have a certain period register starting from the 0 until that period register, but we add one more tick for it for the hardware overhead, and then you multiply it by the prescale value and divide it by the frequency of the instruction cycle. And now we have the equation that controls any timer in PIC 24. It's good to get the value of the period register in terms of the other unknowns. So if the period register is equal to the time of the interrupt flag, the time that you want for the timer to expire, so the amount of the time that you need to wait, multiplied by the frequency of the instruction cycles, divided by the prescale value minus a single clock that we added for the overhead. Now, to understand this, we will see the timer hardware. We will explain each one of them, how to use them, and we will also revisit this equation again. So for our PIC 24, HG128, also the 32 variant, GP202, we have timer 2 and timer 3. We also have timer 1, but timer 1 is kind of specialized. We will discuss it later. But for timer 1 and timer 2, this is the block diagram inside the microcontroller. There will be an external bin in the microcontroller, and this external bin is actually for the timer external clock source. That is, if you choose an external clock source for the timer, you could also have an internal source for the timer. And this is to know the ticks. Since you have ticks, you need a clock source to count these ticks one by one. So if you choose the internal, which is actually the obvious and the cheaper choice, then you need to adjust the multiplexer based on this choice. So you will take the selector's values here to be 0 and 0. So you'll get this value over here. If you have, for any reason, chose the external clock source, then you will have this Schmidt buffer to sharpen the edges, and then you have a block diagram for synchronizing the clock if you need that. Also, you might have other blocks for the falling edge detection when you try to feed up the interrupt flag outside, but this is only if you choose the external source. Usually, we will choose the internal one. So we will put T-gate and TCS to be, or we will make their value 0 and 0. So this way you choose this value over here, and it will be outed in the output of the multiplexer. Now, you also have the T-on, and that's a bit that controls if the timer is going to be on and off. You can see that it is AND gated. So if the timer is on, whatever value here, which is actually the clock of the internal clock source, it will be outed here, and you will have a clock going 0, 1, 0, 1, 0, 1, since the timer is on. If it is off, then you will have either a static 0 or a static 1. You don't have a clock, and the timer will be post. Now, also, it's good to look at this AND gate. You can see that this AND gate, if for some reason you have an internal clock, and also you want to take the external clock, it's kind of a mixture between them. Just you take the AND gate to generate a clock that is kind of at the intersection between these two clock sources, but this is not usually a good option. We usually choose the internal. Sometimes we use the external, as we will see later. So at this point, you go through the pre-scale value. And as I said before, the pre-scale job is to prolong the clock period of the clock source. So instead of having a very short period of time for the clocks, now you will have a longer time for each tick. You have 4 choices. If you choose one, there will be no change. Whatever you have here, it will pass here. We have other 3 choices, 8, 64, and 256, in case you want to prolong it by that much based on your choice. And there is a control for the choices. Since we have 4 choices, we need 2 bits, and it's called the timer clock for the pre-scaler. If you choose certain bits, it will give you one of these choices, and we will see them exactly in a few slides. Now, after you chose the clock, right now here, you choose the ticks are you are getting the ticks as you decided. Usually we choose the internal and we put up an appropriate prescaler value, and now you have the ticks right there. And here we have a comparator that compares the timer 2 ticks that starts from 0 and incremented 1 by 1 to the final value that you registered in the period register, which is the PR2. Once you have the same value here, you compare them and they are the same. If they are equal, now you will reset the timer to roll it over, start again from 0. And also you will generate an interrupt flag telling whatever system that take this output that the timer has expired and now it is counting again. Now, since we choose the T gate and the TCS to be 0, 0, this one will be also going to be 0. So you will have this in the output. Usually we have T gate in all of our exercises and systems to be equal to 0. So we won't touch this block in the future. Now here we said for the whole block diagram here, timer 2 clock, timer or TMR2, PR2, and so on. You would see, for example, here, timer 2 interrupt flag. If you choose timer 3, you can replace every 2 here by 3 for the other timer. Same block diagram, same gates. Also, this is hinted in this simple sentence. Okay, let's go forward. Now, as we've explained earlier, this is the equation that we need to be aware of when we control any timer. The way we get it, we say that the timer 2 interrupt flag, and this flag will be fired once the timer expired. Once the timer started from 0, started to count, and it expires, it's reached to the end that you specified in the period register, or PR2. And at that point, this flag will be generated. So the timer 2 interrupt flag will be the period register, the ending point that you specified, plus 1 tick for overhead, multiplied by the prescaler, the one that prolonged this time now, and you multiply it by a single period, which is the time for the instruction cycle. And by changing the TCY to a frequency, you get this results where the timer 2 interrupt flag is equal to PR2 plus 1 times the prescale value divided by the frequency FC1. Now, again, because timer 2 is 16-bit timer, the PR2 maximum value is 0xFFFF. You cannot exceed this value, which is the 56,553. 2 to the power of 16 is actually have 6 in this digit. But now we are saying 5 because we reserved 1 cycle for the hardware overhead. As you can see here in this hardware, it takes some times to for the interrupt flag to be generated, and we give it 1 clock cycle. So we would say in this example that the PR2 plus 1 will be 56,536. So it's this value, which ends with 35, plus 1, which is going to be this one. If we choose the prescaler to be 1, we multiply by 1. And we have 3 other more choices. We have 8, 64, and 256 based on our need. Now it's your job to find what's the frequency that is running in your microcontroller. If the FOSC is 80 megahertz, then you will put here an FCY 40 megahertz. Since FOSC is equal to FCY divided by 2. So now if you look at this equation here, when you have a timer, usually you know the frequency of the instruction cycle because you know the frequency that your microcontroller run on. You also know the timer rollover period, or you know exactly when this timer should expire. So you want the timer to start from 0, and when it reaches a certain value, you want it to stop. This is the sort of applications you would have in any system. Now, these two values should be known to you, and you have 2 more values that you need to find out. And now we have this equation, which is only a single equation, but we have 2 unknowns, which is the PR2 and the prescale value. So we will rewrite this such that the PR2 will be in the left-hand side, and the rest will be in the right-hand side, as you can see. And this is what we have reached in the first slide when we discussed the time. It's the same thing, but we revisit it again in, from a different angle. So now, how can you solve any problem that you have that needs a timer? If you need a timer, how to find the PR2 and how to find the prescale value. The way to do it is, as you can see here, now the PR2 and the prescale values for this example, if you say that the timer for timer to interrupt flag is 15 millisecond and the FCY is 40 megahertz. So what you do, you know that you have only 4 values for the pre-scale value, or the what we will call it pre from now on. So you have 4 values. You have 1, 8, 64, and 256. This is what you got. So you will substitute for each one of the choices, and you find the PR2 for that choice. As you can see here, I substituted the rollover, or the rollover for timer 2, the rollover time, which is the 15 millisecond. I substituted here, here, and here, and here. Similarly for the frequency, 40 meg, 40 meg, 40 meg, and 40 meg. And now I will one time substitute 1 for the prescale value, 8 for the pre value here, 64 here, and 256 right there. And I calculate. As you can see, for the first choice, when the pre is equal to 1, this is what I got. And I know that this value is more than the maximum that timer 2 can handle, which is 2 to the power of 16 minus 1, 56,535. So the this pre value, which is equal to 1, is invalid. I cannot represent this number in only a 16 bit register for the period. Remember, this is the value of the period register. So it's only going to be 16 bits. That's the maximum. I cannot represent this in 16 bits, so it's invalid. Similarly, for the 8, if you substitute, you will find a value. It's close by, but still bigger than the maximum limit. It's still invalid. For the 64, you'll find this value, which is between 0 and the limit. So it's valid value. Similarly, if for the 256, it's also valid. So again, we say invalid because it does not fit a 16-bit in the PR2 register value. We usually pick the lowest prescale value, in this case, the 64. So we will choose this one for the prescale value. If you pick the pre is equal to 64, then for sure, the PR2 is going to equal 9,374. So now you can imagine the timer. How does it work? It will start by 0, incremented by 1, 2, 3, and so on, until it reaches to the 9,374 tick. And at that point, the timer expires and it generates the timer to interrupt flag. And this time will be exactly 15 milliseconds, since we already calculated. Now, how fast these ticks are generated? It's generated based on this frequency, which is the 40 megahertz. Now configuring timer 2 to interrupt every 15 millisecond in our case, this would be called a periodic interrupt because it will interrupt every time. So it gives you the interrupt, reset the timer, start from 0 again, and count until you reach to 9,374 ticks, and again and again and so on. So we call it periodic interrupt. And we will have more examples to understand these results. Now, let's move forward. This is a timer 2 control register. This is a special function register. And from now on, actually, we've done this in the previous lectures. Every module has its own special function registers that controls it. Sometimes it has also status register to tell you what is the status of the module. For the timer 2, we have only a control register. It has these bits that you can see here. The others are unimplemented or not used. So we will consider them zeros. For the TCS, which is the first bit, this is timer 2 clock source select bit. And we said that we will make it 0. We will make it 0. Write it. Now let me write it down. We will always choose this to be 0. And also the T gate, we'll choose it to be 0. The reason is for this choice. We said that we will say 0, 0 here for the internal timer clock. So we will fix them to be 0. Also, the T gate here must be 0 for the interrupt flag passing to the output. Also, here we have T32, and that's the 30-bit timer mode select bit. So far, I explained to you only when we have a 16-bit timer. We can actually have a 32-bit setup, but we've not reached to it yet. So we will choose this value to be 0. And now here is our choice of the BRI value or the BRI scheme. We have 2 bits, and now you know exactly for if you choose 0, 0, then the BRI scalar will be 1. If you choose 0, 1, the BRI scalar would be 8. If 1, 0, the BRI scalar is 64. If it is 1, 1, then the BRI scalar is going to be 256. And you can also see them as binary values, or you get their decimal. So this will be 0, this will be 1, here we will have 2, and here we will have 3. So it's based on your choice. You will have the setup for this prescale value. Now, notice so far, I want to break this down like this. Here we have one hexadecimal digit, 4 bits. So for our choice, it will be always 0. If we assume that we will choose only 16-bit timers, it will be always 0. Now for this one, for this digit, it could be 0 or 1 or 2 or 3 based on your prescale selection. Now for the next hexadecimal digit, it's always 0. And for the last one, we have 2. One of them is the TSIDL. This is the stop in idle mode bit. We will always assume that it's going to be 0. So we continue the module operation in idle mode since we didn't reach to the idle module yet. We will talk about this later. And even when we reach to it, we will never change this. Always when we have an SIDL, whether it's a timer or any other module, we will choose it to be 0. There are some application for it, but it's not that critical. So we will choose this value to be always 0. And for the last one, which is the most significant bit, and you will notice this in other modules as well, it's the on bit. This is the timer 2 on bit. So if it is 0, then the timer is off. If it is 1, then the timer is on. When we configure the timer, we make it off at the beginning. So at that point, this hexadecimal digit will be also 0. So from this discussion, we know that if you choose the prescale value, the control register will have either this value, which is 0x0000, or 0x000100, or 0x0200, or 0x0300. These are the three possible control register values, given that we choose an internal clock source, which is the obvious and the most or the cheaper choice, and always given that also that we use only 16-bit timer. So these are the 4 values based on the prescale selection bit. Now let's move forward. How to program the timer 2 control register. You can write the 16-bit value for this special function register. This special function register, it has a name. This name is T2 control, or the timer 2 control register. We also have timer 3 control register for timer 3. So if you choose timer to configure timer 2, it will be like this. T2 control register is equal to 0x0200, and as we discussed, this 2 means that the prescale value is 64 and the timer is off, and also we choose the internal clock. There is another way. I don't suggest that you go to that way unless you want to change bits more frequently. So for in the timer 2 control register, usually we will set up the control register for timer 2 this way. The other way is actually for each bit or each group of bits that you see here, for each field, it has its own name. So we have timer 2 underscore off. We have timer 2 ideal control, timer 2 gate off, timer 2 32-bit mode off. This means for each one of them that the value is going, since we chose off, and off, there is another value with on. Since we choose off, then the value is going to be 0 for each one of them. And then you OR everyone together and you generate the same timer 2 control register value. The only one that we need to worry about, and we will use it many in our programming from now on, is at the beginning, since we choose 0 here in the most significant digit, this means that the on value is going to be 0. So once we're done with configuring the timer 2, or configuring our whole system, add one of the last statements should be making the timer on. And to do this, you would say timer 2 control bits. Notice that this name is the same as this name. We just added bits after that. You would see this in many other special function register or SFRs. So be aware of this. Since you say timer to control bits, after that you enter dot, and as you know, in object-oriented, you will have all of the bits of the timer to control register, including all of these bits. This, and this, and this, and this. Sometimes on, sometimes off, based on what we've discussed here. So here we have the T on, and you could say that now T on, which is this field exactly, is equal to 1, meaning that now you are setting the timer to be on. And now the timer will start working from 0, 1, 2, ticking all the way to the period register. So let's have an example so to understand all of what we've discussed so far. If you were asked this question, given a big 24 processor with a frequency of oscillation 80 megahertz, what is the value of the timer 2 control register and the period register of timer 2 in decimal in order to generate an interrupt every 0.25 seconds or every quarter of a second? That's the first requirement. And then based on that, write a code to use this signal for generating a waveform with a specific frequency. He chose in this problem that the frequency is equal to 2 hertz. 2 hertz. And he wants also this waveform to be generated at port RP5. You can see now we are working with timer, and also we are touching the GPIOs that we've discussed before. So we know that this is our predominant equation that control any timer. Also, we need to generate FCY because we have FCY here in the numerator. So you have FCY. You get FOC, which is the 80 mega divided by 2. Since we know that every instruction needs 2 clock cycles to execute. So FOC divided by 2 is equal to 40 megahertz. And now I know that the rollover time or the expiring time of my timer is 0.25 seconds. So I multiplied 0.25 seconds by 40 mega, and then I set up my choices for the pre-scale value. We have 1, 8, 64, and 256. For each one of them, I generated the period register value. Here it's invalid, obviously. Here also we have a big number, so it's invalid. For this one, it's getting closer to the 65,000 plus 535 ticks. So now also this one's still bigger than that, so it's invalid. The only valid one is the 256. 256. It generated 39,061.5, and that's valid. Now the PR2 register is an integer value, should be an integer value. We didn't specify any floating point in any of our program up to this point. So we always talk integer. So what I did here is I round it up. So it's going to be 39,062 for the PR2. And I know my prescale value is 256. Since it's 256, I can right away know that the timer 2 control register is going to be this way. Because I know that hexadecimal digit, based on our discussion, is going to be 3. So I didn't choose 0 or 1 or 2. I chose 3. So that's for the timer 2 control register, and the prescale value is 256. The breakdown of the timer 2 control register, if you want, you could say that the T gate is equal to 0, that T32 is 0, the TCS is also 0, and the TSIDL is also 0. The only one that we worked on is the prescale value, which is going to be 1 and 1. And from that, you get the timer 2 control register to be this value. Also, the on value, the beginning, we will make it 0, and then later we will set it to be 1 once we finish setting up the time. So to write the code to do this, or now we set up the timer 2. We know the PR value, which the PR2 value, which is this one. We also know the timer 2 control register, which is also the pre-scale value within it. So we know all the specification that we need for the timer 2. Now we move to writing the code. So the following code generates a waveform with 2 Hz frequency at port RP5. Notice here in the main, you could have actually a method for the configuration by itself, and then you call this method, or you could write it down right away in the main, since it's very short for a single time. So you say timer 2 control register is 0x0300, as we've explained. The PR2 is equal to 39062, which is also calculated. Now for RP5, I need to set it up to make it an output, because I'm generating this waveform. So the tris P5 is equal to 0, and its lat B5 is also equal to 0. And I set up the output based on the discussion that we had before. I need to make sure of the analog signal. I need to make sure of the ODC and the pull-up enables, all of these. But it's not our subject here, so quickly I choose the default values here. Now, it's very important to know, for any timer when you start it, you must set the flag to be 0. This flag will be asserted to 1 once the timer expires. When the flag is equal to 1, it tells you that the time started from 0 and reached to the PR2 value, which is in our case, this value. After this setup, the last statement you would say, okay, timer, start. So you'd say timer 2 control bits dot t on is equal to 1, and now we start the timer. Now, to generate this waveform, this is the way to do it. We would say while 1, if timer 2 interrupt flag is equal to 1, then you do some jump. If it is not, keep waiting. Because I know the flag will be equal to 1 if I start the timer at 0. So, and also I make the lat B5 equal to 0. So now I'm observing RB5 at the board, and the value is 0. It will remain 0 for 0.25 nanosecond for sure, because I set up the timer for this time. Now, once you have an interrupt flag, I will reset its value, preparing for the next time I'm generating an interrupt flag. So once it's 1, I know that. Thank you. I reset it. The first thing, and this is one of the programmer's responsibility. Whenever you have a flag, remember, we don't have an operating system in this microcontroller. So whenever you have a flag, your job as a programming to reset its value. And at this point, I can toggle the value of the RP. So now I toggle it and I make it 1. It will again, through the while loop, remain 1 for 0.25 second, and this repeats. As you can see, now for 1 cycle, we have 0.5 second in the time. Since this is a half, if you take the reciprocal to get the frequency, then the frequency is going to be 2 Hertz, which is the required value. This is the way we've done this. again, one of the key things that you need to remember is resetting the flag when you start, and whenever the flag is risen, meaning that the timer expired, again you reset the flag. Okay, let's continue. More examples. Now here we say, given a big 24 processor with another frequency of oscillation, 6 mega, what's the value of the timer 2 control register and the PR2 in order to generate an interrupt every 2 seconds? So our time now is 2 seconds. And then based on that, write a code to use timer to interrupt flag to generate a single high pulse. Now it's not periodic anymore. I want a single high pulse, and its width is 2 seconds. And I used RB9 here. So at this point, same thing, just I change the values here. The FCY is going to be 3 megahertz since I have 6 megahertz here. And I have again 1864 and 256. I plug in the value that I'm for my timer, the value when it's going to expire. So I plug it here, 2222. The 3 mega is over there, and I test each one of the prescale values. This is invalid. This one will be invalid. This one also will be invalid, and the valid one only is the 256 again. So the timer 2 control register, same scenario, is the same value, and the pre is 256. The only change here is the PR2, since I have now 2 seconds. I have 2 seconds, so I have this value. Again, it's rounded. So how to generate the waveform? I write the code this way. The setup is exactly the same for the timer. Only we change values now based on our calculation. So I have timer 2 control register. I have this value now. I have another port, the RP9. So I make it 0. The trace is 0 for output, and the lat value, the first value is going to be 0. And this 0 should be 0 for a certain period of time that is equal to 2 seconds based on my setup. And at this point here, I start of course, I reset the flag, and then I start the timer. Now the timer will start counting. Now here I say, while the interrupt flag is equal to 0, get stuck in this while. This semicolon, right after the while, tells you that you get stuck here until the interrupt flag becomes 1. And then you can continue. So when it becomes 1, it means that you already passed 2 seconds. It was 0 for 2 seconds. And now I reset the interrupt flag again because you got out when it was 1. So I reset it again. And then I make the value of the latest value of port 9 equals to 1. So now it's 1. This is in RP9 for 2 seconds. It's 1. Actually, I got the 2 seconds from the second one. From this one. Again, I wait the same thing. I wait as long as the interrupt flag is equal to 0. It will becomes 1 when I pass 2 seconds. And after that, I get out, and now I set the lat p value equal to 0 after resetting the flag. And after this, I stop the code. So at this point, it will remain 0 forever. And I have a single bus of this width, which is the 2 seconds, which is the 2 seconds. That's the way to deal with a time. Now, at this point, you know exactly the hardware inside a microcontroller and how to program timer 2. But we never touch any interfacing. And the reason there is no interfacing because the timers, timer 1, 2, and 3, they are internal modules that you don't need to interface it with the microcontroller. It's inside the microcontroller itself. Actually, when we define the microcontrollers in the first few lectures, we said that a microcontroller is the CPU plus the other modules. They are all together considered a microcontroller. So this microcontroller is actually inside this timer is inside the microcontroller. So you don't need to interface. The only interfacing point here is the usage of certain ports, like the RB9 in this example, and the RB5 in the previous example. That's the only ones. Now, let's continue more discussion of the timer. What if you need a 32-bit time? Up to my knowledge, in our class, the whole class, I don't think we will reach to a point that we are forced to use a 32-bit time. But just in case, if you were forced to do this, you can see that we have the same hardware here. We have the same prescaler value. The only difference here is now we concatenated the period registers, PR2 and PR3 together. And now we have 16-bit here and 16-bit here. So the total is going to be 32. And this way we have a 32-bit time by concatenation. Similarly, we will have the TMR3 and TMR2 as well. So it will start from zeros. You zero out all the 32 bits and then start 1 and 2 and 3 until you reach to the period register that is supposed to be more than 2 to the power of 60. Because if it is less than that, then one PR register is enough. So it's supposed to be more than that. So now you compare again, same scenario, and then you reset and you send your interrupt flag. What are the differences? One of the differences that you can see that if you choose an external clock for the combination of between PR2 and PR3, so actually I should have mentioned this in the beginning. What we mean by a 32-bit timer is the combination of timer 2 and timer 3. So we add them together to get a 32-bit timer. So if you choose an external clock, it's going to be the timer 2 clock. That's the name that you are going to use. That's what we said here, combining timer 2 and 3 into a single 32-bit. Timer 2 will be the least significant word or the least significant 16-bit word. Timer 3 will be the most significant 16-bit word. Timer 2 control bits are the timer 2 control register. So since we combine, we pick one of them to be the control register, and we pick timer 2 control register. The flag is T3 interrupt flag. So the flag will be the timer 3 interrupt flag that you will use it for when your timer expired or roll over. And the period register, as I explained, is the concatenation between both of them. So these are the differences in the names, which name that you are used. Usually you should be worried about the usage of the timer 2 control register and the timer 3 interrupt flag. So when you configure the timer 2 control register. When you check, you choose T3 interrupt flag in case you use a 32-bit timer. Other than that, some other things that you need to worry about is you know that your data bus inside the microcontroller is only 16-bit. So now you have a 32-bit value. What to do? You send the value in either direction, whether you are reading or writing, into 2 steps. So in case you are writing, you write the most significant bit, 16-bit first, the most significant 16 bits or the most significant word. You write it first, and then you write the least. So this is why we have a hold register here. So whenever you are holding this value, at the beginning, you heard that you are holding the most significant word here. And then whenever you are reading the least, you also upload the held value. So in the same clock, you have the 32-bit residing right there. For the reading, it's going to be the other way around. So let's check this as well. This is what will happen. This is one of the application of the union that we described first. And when we talked about the C language. So the union structure is basically the sister of the struct data structure. So you say type def union underscore union 32. So it has three ways of doing the same thing. Either you take 32-bit, that's the type, or you will take two 60 bits as a struct. So you have a least and a most 16 bits, and or you will have 4 bytes for different parts. So a 32-bit, either you will take it all as a 32-bit, a whole, or it will be 2 half words, or will be 4 bytes. That's the definition here. This is what we worry about the most when we use 32-bit. When you write and when you read, so if you have a written value that you want to write, or you want to read a value, this read value. So the write value, which is, if we say that this is the right value that we want in hexadecimal, notice that it's 32-bit. In the hold, notice that in the write, we write the most significant and then the least significant. So the most significant words first. So you go write value dot U16 to get to access the most significant, and then you put it in the hold register. And after that, you write the least significant, which is the U16, and then the least significant. And you write it to timer 2. And the hardware will take care of the rest. For the read, it's the other way around. You get the timer 2 value of 2, which is this value first. So you get this value first, and then you load the whatever was held in here. So that's what we have, the timer 2. You put it in the least significant, and the held value, you put it in the most significant. This is the usage of the 32-bit. Again, it's not always the case. I think from now on, we will never use the 32-bit timer at all in our class. It's only in a very specific cases, and usually if you need a timer that has a bigger period, you choose a microcontroller that supports that. You don't stick with the big 24. Now for timer 1, when we start discussing, we discuss timer 2 and 3. It's like there is a jump. We didn't touch timer 1 first. Why? Because timer 1 is very special timer. It's a 16-bit timer, same thing. It can be operated only from the low power 32 kilohertz. So it's from this frequency source, which is a 32 kilohertz. And we will revisit this when we talk about the oscillators in another lecture. For this source or clock source, we choose an external source. Now we don't use the internal anymore. So we don't have a 0, 0 here. We don't use the internal. We use the external source. So the external source is a crystal. This crystal oscillates with this frequency, 32 kilohertz. And again, it has a prescaler value, the same thing. And now, whether you want to use a sync or not, you choose based on this choice. And here, we should choose this 1. So the TCS must be 1, and the T gate is a don't care, so we could make it a 0. And now you have this choice, which is the external clock for the timer. And again, you have a comparator, and if they are equal, it will set the flag and reset the timer as a rollover again. So you can see that the hardware is very similar to that hardware that we discussed before. Same block diagram, even for the other parts. The only change here is timer 1 application. Where do we use timer 1? We usually use it for the read time clock, or the RTC. Sometimes they call it real-time clock as well. So that's what we use it for. It's actually for the clock that you use in your everyday life. That starts with 1 second, incremented 2 seconds, 3 seconds, 4 seconds. And from that, you can get the minutes, the hours, the maybe also the day, the month, the year, all of it. So to get that, you should use a certain timer. If you have a subsystem and you worry about the time, the real time, then you use timer 1. Now, how is this happening, or why we are calculating it like this? Before we move from this slide, actually, I should mention that timer 1 cannot be operated in a 32-bit mode. And usually we use an external clock, as we mentioned. So we cannot combine it with any other time. Also, this frequency is actually, this is like a rounding for the clock. It's actually 32.768, and we will revisit this when we talk about the oscillator. Now let's continue. What about the control register? Same thing as timer 1 and timer 2. Now here you should use the external clock source for the TCS. So this value will be 1. For the T-sync, depends on if you want to synchronize or you don't want to synchronize. If you do not want to synchronize the external clock, this value would be equal to 0. The prescaler, same discussion that we've talked about before. The T-gate, this value should be 0, since we said this actually, I don't care. So to match it with our previous configuration, we will assume it's going to be 0. For the TSIDL, it's going to be 0. And for the T on, it will be 0. And then we will make it 1 when we are ready. Now, how can you do the real-time timekeeping? You do it this way. What is the usage of this time? This is, by the way, the crystal that I just mentioned. This is the external clock source. That's one example for it. Also, you can see that the frequency is actually typed in within the crystal itself. So the 32-bit or the 32.768 kilohertz watch crystal, which is this one, if you choose the PR1 to be 0xFFF7, this means that the timer period is from 0 all the way to this value. So since we started from the 0, you would have in hexadecimal format 0x0008 ticks, which is basically 2 to the power of 15. And you can't get it right away from this value. If you have F, 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 and F, we said that this is 2 to the power 16 earlier. So if it is 7 here in the most significant hexadecimal digit, then it's going to be 2 to the power 15. And 2 to the power 15 ticks, that's 32,768. So that's the amount of ticks that you can have for this timer. And the frequency that you work with is very similar. So from that, you can actually get 1 second for a 32.768 kilohertz. If you make your PR1 equal to this value, which we have written down in your code, and you use timer 2 control register to be 0x2000, meaning the prescaler is equal to 1. Now, the setup for timer 1 control register, it would be 2, which is 0100. We have this one now for the TCS, which we said here. We make it 1. And for this, the rest of the values, now this is the 2 here, the 2 in hexadecimal. And for the other values, all 0. Since the T gate is 0, the prescaler is 0, all other values going to be 0. So now we configure this timer 1 control register and the PR1 value. And now I can count the seconds. From this specification, I can count the seconds. And you can get it even by the values that, or if you apply this equation that we have here, but now for PR1, you will end up with the 1 seconds in the PR2. So every time you have an expiring interrupt flag, it means that 1 second has passed. So you start the seconds from 0, you reset the interrupt flag, and then you start the timer. And you go while 1. If you have an interrupt flag, it means 1 second has passed. So you reset the interrupt flag and you increment the number of seconds, and you can display them if you like, and you go and do this for as long as you want. So that's the job of timer 1. It keeps a record of the real time. If you chose to build a clock or a digital clock, or what we call here a real-time clock or a calendar module, you can use timer. So you have the external crystal, you have this oscillator that we talked about, you have the prescaler value, and it gives you 1 hertz. So 1 hertz means, and the period, your period is 1 second, since the reciprocal is also 1. And you can accumulate these seconds that you accumulated here, and you put it in a structure with seconds, minutes, hour, week, days, a date, a month, a year, and so on. And each one of them, you can figure them out. It's very easy. Like for the seconds, it's from 0 to 59, the minutes from 0 to 59, the hours from 0 to 23, the weekdays from 0 to 6, the date from 1 to 31st, the month from 1 to 12, and the year, in this case, from 0 to 99. And you can make use of this available to extend this to more than 2000 when the year that you have is more than 1999. And now you have the RTCC, which is the real-time clock calendar module this way. You also could have side by side an alarm, same setup, but usually you don't set up the alarm for a year. That's the maximum they give you is a month. Even the month, we usually don't use it as a human being. And we can compare these two values, which is the real-time clock value with the alarm value. If they match, then you set up a certain flag and you probably generate an alarm. So that's the idea of the RTC. At this point, we finish the timer discussion and we will move to the output compare module. Now, just by looking at the name output compare module, you might not understand what's the usage of the output compare. We will explain it in detail, and you will notice that you cannot have an output compare module without a timer. And that's the reason we discuss the timer first, and after that, we talk about the output compare. So let's define the output compare module. The output compare module is a peripheral that generates pulses of a specified pulse width and a period on a certain pin. This pin is going to be named output compare X. Maybe you have 1 output compare or 2 or 3 output compares on your microcontroller. For the BIC24, it has 2 output compares, and usually we only use one of them, output compare 1. So the idea about the output compare, it's giving you or outputting a pulse. This pulse might be of many shapes. They differ from each other by width, by period, and so on. So how to identify them? We use an output compare mode bits. There are 3 bits to distinguish between the type of the signals that the output compare module can generate. One of them is the active low one-shot, the other active high one-shot, the toggle, the delayed one-shot, continuous pulse, and the critical one, the most important one, and the focus of this lecture is the pulse width modulation signal, or the PWM. As you can see, here is the code for each one of them using the OCM. For the pulse width modulation, it's 011 or 111. There is a difference between these two. One of them support fault detection and dealing with faults. The other one doesn't support any fault mechanism. So our choice will be the one without fault, which is the 011. That would be pulse width modulation signal generated by the output compare module. Now, as we've just said, that the output compare module uses timer 2 or timer 3. It must have a timer, or you need to define a timer. You need to configure it and program it before you before the output compare could work. So the pulses are output on an external processor bin controlled using the 3 registers. So there we have 3 registers associated with any output compare module. The first one is the output compare 1 control register. So that's very close to what we've said about the timer. We have timer 2 control register and timer 3 control register. Here we will have output compare 1 control register and also output compare 2 control register. From now on, we will only talk about output compare 1. Now, also you have 2 registers associated with the output compare module. We have the OCR and the OCRs. So the first one is the output compare register, and we have also a secondary register. Now let's see what do we mean by these different signals, and then we will show you that the pulse width modulation is actually a general wave form that could also include all of the previous ones. So let's see. As you can see here, we defined a timer. The timers goes or start from here all the way, start counting all the way to the rollover time, or when the timer is resetted, and then it goes back again, and you count in the timer until you reach to the PR2 or PR3, the period register, and then go back again, starting from 0 to the maximum, and so on. So it's periodic. And you can see that at a certain point, you will hit the OCR, whatever value you put in the OCR register, you hit it first, and then after that, the secondary register or the OCRs. So based on these 2 points, it defines the types of the pulses. The first one, the active low one shot, you can see that it starts with the beginning of the timer, and the pulse ends with the OCR. For the active high one shot, the start and the finish is the same, but it's the other way around. For the toggle happens at the OCR point. So whenever you hit OCR, the toggle happens, and so on. For the delayed one shot, you can compare it to this one. It's the same thing, but the beginning and the end is different. The beginning, it begins with OCR, it finishes with the OCRS. The continuous pulse, we have a continuous pulse instead of only this one, which is only one shot. You have a continuous pulse. It started with R, finished with RS, again R, RS, and so on. For the pulse width modulation, it can begin and end based on your choice. Also, it doesn't have to be the exact same pulse periodically. It depends on the value of the OCRS, actually. To understand the relation between OCRS and OCR, let's see the hardware. So again, just to remind you before we go, the PWM, we choose it by the OCM bits. And to specifically choose the PWM, we put 0 and 1 and 1. Okay. So the hardware here is actually, here's the timer. You have timer 2 and timer 3, or TMR2, TMR3. This starts from the 0 and start incrementing. It depends on whatever you choose. Sometimes we choose timer 2, sometimes timer 3, based on the availability. And here we have the rollover, or what we called before, is actually the same as PR2 and PR3. It's the same one. So you select one of them. Let's say that we selected timer 2. So we select this one and this one. And you start counting. Now, the counter here, at certain point, it will hit the value of R. And after a while, it will hit the value of RS. And this is why we have a comparator here, and you compare. Whenever you have an equal value, you will send this signal, which tells you that they are equal, to the output logic. And the output logic also accepts the timer to roll over to knows exactly when the timer reset, and also the ECM to change or to have all the modules. Of course, here we will choose 011 since we fix the PWM pulse. And other than that, from this output logic, it outputs an output compare interrupt flag when it is ready. After that, of course, the output that we want to have is the pulse itself with a certain period. So your pulse will be generated right there. It depends on the pulse that you want to generate. Doesn't have to be a clock. It can be anything. If you look at the BIC24 bin diagram, you will never find a bin for the output compare. And this is why we need one of the RP pins or the RP boards to assign it to the output compare. And we will show you how to do this when we talk about the programming. Now, this hardware is kind of, there's so many buffers here that you need to enable and things like this. Basically, the buffers here, you have many choices. Either you feed the RS directly to the comparator, or feed the R directly to the comparator, or make the RS value go to the R first, and then the R is affected, and then it goes to the comparator. There are many choices here, and it's based on whatever you are having from the output logic as an output, the feedback over here. So that's what we have. These or the OCFA, OCFB, and so many. It's not for BIC 24 that we used. It's for other BIC 24s, and especially if you have more output compares. But we will skip this. We are not going to use it for our microcontroller. So here, the pulses are generated on the output compare pin here, as I specified. But for our microcontroller, this one, it doesn't have this. It has only two output compare, and we will focus on output compare one. Also, the OCR registers controlled when the output pin is affected by comparing against either timer 2 or timer 3, as we specified here. Now, let's simplify this. Since we are not going to have all the OCMs, we have only one of them. So we can skip the output logic and some of the feedbacks here to clarify the hardware. And this is a simplified version of it. As you can see here, now we chose that the OCRS will feed OCR, and then the OCR will feed the converter. So basically, the OCRS becomes the master, and OCR is just a slave. Whatever the value of the RS, it will be fed to the OCR. And again, you will have the comparator for these two muxes based on the output compare timer selector, whether it's 0 or 1. Here you have the rollover or the period register, and here you will have the value that's ticking starting from 0 all the way to the rollover time. So the ticks happens here, and you have a comparison. Whenever you have a match, it will set this flip-flop, and then it will be fed to the output compare pin. So this is kind of an easier view of the hardware. After the block diagram, now to understand how the pulse width mode or the BWM could be changed based on our choices, let's have some examples. So here we have two examples. To understand this, first, we have the value of the OCRS, and then we have two cases, case number 1 and case number 2. In case number 1, we set the OCR, and also in case number 2, we set its OCR different. So they differ from each other, as you can see here. Sometimes, well, like the value here is 20, 50, 0, and 20. The value here, it started with 0, which is different than the first. And then it's the same, 50, 0, and 20, and so on. We said that the OCRS is the master and the OCR is the slave. And this is what we have here. The 50 here will be reflected back after some times in both of them. Similarly for the 0. Similarly for the 20. And so on. So what's going on with this? Also, to understand the full picture, here we have the timer. The timer starts from 0 all the way to the timer rollover, and again 0 to the timer rollover, and so on. Now, for the first case, since we choose the beginning differently than case 2, so here we have 20. And that's why we have a pulse starting from this point all the way to 20. And then it goes back to 0. And then from the beginning of the timer all the way to 50, which is this value that we copied from the RS. And then again, until we reach to the actually, we should be checking here, but here the value is 0, so there is no pulse, high pulse generated here. And then again, we have 20 and so on. For the other signal in case 2, from here onward, it's the same. But before that, the value was 0. This is why we don't have a high pulse here. Basically, the general idea here, the value of the RS is affecting the high time. So if it's 20, we have certain value. If it's 50, more than that. 20, it's shorter, and so on. So also, just to understand the full pictures, here we have some numbers indicated some events. So in the number 1, the duty cycle of the first pulse width modulation cycle is written to the OCR register before enabling the BWM mode. For the second, which is this point here, here we fed the R. You can see that we have the value of the R here. And 2, we have the value of RS. The duty cycle for the second BWM cycle is written to the OCRS. And number 3, which is here, the BWM mode is enabled. So the output compare pin is driven low if the OCR is 0 the OC pin is driven high if the OCR is non-zero. So the OCR here is non-zero, so it's driven high. Here it's 0, so it's driven low. 4, the timer is enabled and start incremental. So as you can see here, we started the timer. For 5 on the compare match, and this is why we call it output compare. So in a compare match, the OC pin is driven low. That's in number 5. So we hit 20 here, so we make it low. Here is actually low from the beginning, so it's continuous low. Number 6 on timer rollover, which is right here and here. The OC bin, on timer rollover, the OCRS value is loaded into the OCR register. So again, we are talking about the OCR. The OC bin is driven high if the OCR 0 and low if the OCR is non-zero, as we've specified. Here, it's non-zero in both cases, so they are driven high, and they will remain high until the value of the R, the OCR, which is the 50 in both of them. The 4.7, the 0.7 here, it just tells you that the duty cycle of the third pulse width modulation cycle is written to the OCRS register. So at 7, we are changing the value of the OCR S, and we continue to do this, and so. Now, it's very important to tell you, I'll go back here to this hardware. Since we choose the pulse width modulation or the PWM, and we have this mode, 0, 1, 1, since we make these choices, the only thing that we need to choose more than that is the output compare timer selector. That's the only bit that we need to adjust other than the PWM mode. So if you choose 0, that's timer 2. If you choose 1, that's timer 3. Also, another critical piece of information here is actually we need to write the OCRS only, because for the PWM, OCR will always follow the OCRS. So we are not going to adjust the OCR at all. We will just give the value for the OCRS, and in turns it will be passed by hardware to the OCR. So now, after understanding what's going on with the OCRS, the conclusion of all of this, if you set up the value of the OCRS, you can set up the high time. You can set up the high time, and you can see that this value is affecting the high time if you exclude the beginning, and that's very important. Let's see this effect. If we know that the pulse width mode period, actually any period, will be the PRY plus 1 multiplied by the TCY multiplied by the Brie scale. And we know this from the timer. That's for any period of time. If you want to wait for 15 milliseconds, if you want to wait for 2 seconds or whatever. Same thing for the pulse width modulation period. If you want a certain period for the PWM, meaning this time, this period, then you can apply the same thing, where you can find PRY by doing simple mathematical manipulation, and you have the same equation that we reached in the timer. It's the same thing. The only one thing that we changed here is we gave the time, or the timer to interrupt flag that we had before, we call it PWM period now. And the other things are the same. So now we define the period. Let's also define the high pulse time, the one that is affected by the OCRS. So the high pulse time is actually this time here. And it's going to be the value of the OCRS multiplied by the TCY multiplied by the Brie scalar, which is kind of the same here, except that instead of having the period register, which is the maximum reset value of the timer or the rollover time for the timer 2 or timer 3, now we have it before that, which is the OCRS. RS. And notice here in the figure, OCRS is always less than that. So you can have it also shown clearly here. If that's the period register, OCRS is less than that. This is the period register, OCRS is always less than that. So now the high time, the one that is affected by the RS, instead of the timer, we have it for the OCRS only. And now we can get the duty cycle percentage, or what we call duty percent. It's actually the relation between the pulse width, TW, and the time or the period here, T. So TW over T multiplied by 100 give you the duty percentage. Now the TW is actually the high pulse time, and the T here is actually the pulse width modulation period. And we already defined these values here. We can plug their value, and then we cross out the what you see here. We cross the TCY and the TMRY prescaler value, and we end up with this result. And this result shows you that the duty percentage, or the duty cycle here, is directly affected by the OCRS. So now, as we said, we define the duty percentage by the ratio between the high time and the full period. So the more duty percentage you have, it means more high time. So just to give you an indication by this, let's go to this figure. Here, if this is the whole period, this would be about 20% or maybe 15%. So if you have 20 or 15%, the OCRS value will be, according to this value, it will be less than, say, 50%. If you have the whole thing here, then the value of the OCRS should be more than this value. So if the period here is 100 nanosecond, let's say, so this value will be maybe 20. This one will be 50. That's the idea here. So we reach to this conclusion again. The value of the OCRS affect the high time. If you increase the value of the RS, you will increase the value of the high time. Now, going back to the output compare control register. The OCM, we fix it. We said that we will choose the 011, which is the pulse width modulation mode without fault protection. You can check the others as well. So we make this 0, 1, and 1. The output compare selector, it depends which one of the timers do you want to choose, timer 2 or timer 3. So sometimes it's going to be 0. Sometimes it's going to be 1. Let's have a break here. The OCFLT, which is this one, we will choose 0. No pulse width modulation fault condition has occurred. We will assume that there is no fault. So it's going to be 0. The other bits, as you can see, they are all 0. And the SIDL, like the timer for the output compare SIDL, since we are not going to touch the idle mode here, we will consider it also 0. From this discussion, we say that we only changing this bit based on the timer, whether it's timer 2 or timer 3. So you will have two options for the output compare control register. Either it's going to be 0x 0110, which is 6 0 0 0, or it's going to be 0111, which is going to be E 0 0 0. In decimal, this is actually 6, and this is 40 in decimal. If you want the value in decimal. So to set up the output compare, it's fairly easy. It's actually easier than the timer. So let's give more examples to understand what's going on here. We have the pulse width modulation. If we chose that the output that is generated by the output compare after we configure it and program it, we connect it to a LED with in series with a resistance to make sure it doesn't burn. And we have a certain pulse width modulation. Now, if you plot the relation between the duty percentage or the duty cycle and the current running through the LED, you can see as the duty cycle increase, the current will increase in a linear fashion, as you can see here. Meaning, if you increase the value of the output compare or the OCRS, the duty cycle will increase, and based on that, the current will increase. Now, if the current increases here, it means that the intensity of this LED will also increase. Remember, this is a pulse width modulation signal, so it goes 1 and 0 and 1 and 0 and 1 and 0 in a rapid fashion, because it usually has a higher frequency than what the eye can catch, what your naked eye can catch. So instead of seeing the LED going 0 and 1 and 0 and 1, you will see actually the intensity of the light is decreased. So now we see that a good relation here is imagining that, or the relation is actually, if the output compare high time increases, the current will increase. And whatever you are connecting this output to, whether it's if it's a LED, then the light intensity will increase. If it's another system, the current running through that system will increase, and based on that increase, it will affect the system in a certain way. So let's have an example to understand this better. Here in this example, we say write a code to configure and use the output compare module for controlling a LED in an 80 megahertz processor. The system has two switches. So you have two switches, one called an increment switch, and the other is a decrement switch. When the increment switch is pressed and released, the intensity of the LED increases. And for the decrement switch, will decrease the intensity of the LED. And we select the pulse width modulation frequency to be 200. So usually you have two frequencies here. One for the microprocessor of your microcontroller of the PIC24, and the other is for the pulse width modulation. And the pulse width modulation frequency should be much less than the frequency of the processor. Now, also assume that the following function is already there. We configured the decrement switch already, also the increment switch, and this is a GPIO configuration, and we learned this previously in the previous lecture. We have also decrement switch is press and release, and increment switch is press and release, and those two methods return one of the event happened. For example, this one, return one of the decrement switch is pressed, then release. Okay. Let's try to solve this. So we start by setting up the timer. Same way to what we've just talked about in the time. So we have the PR2 equal to the pulse width modulation period times the FCY divided by the pre minus 1. And the FCY is the FOSC divided by 2, which is going to be 40 mega since we have 80 meg here. Now we found the prescaler or the appropriate prescaler that we want. From this, we plug in the value of the PWM period. You were given a frequency, so you say that it's 1, or take the reciprocal of this 1 divided by 200. That's the period of the pulse width modulation. And the 40 mega is our 40 mega, and you one time substitute the pre when it's 1, when it's 8, when it's 64, and when it's 256. And calculate the period registered for timer 2. So now we chose timer 2. It doesn't say here to choose timer 2 specifically, but we chose it. We can choose 2 or 3. Here we chose 2, since we call PR2 or the period register 2. And now this value will be invalid, and we have 3 valid values that can be written in a 16-bit PR2 register. So we chose 3124, which is this one. And for the timer control register, we know that we chose this one. So we have 64 as a scalar. So the timer to control register will be 02. This is matching the second choice number 2. This is choice number 0, number 1, and this is number 2. So this is 2. And this is our choice. This way we set up the timer completely. Now for the output compare, we have only 2 choices, either this one or this one. So since we choose timer 2, our output compare control register will be 0x600 and 0. And this is what we have in the program. So as you can see, we configured the output compare, we configured the timer first, and then we said that the output compare control register is equal to 6. Now, other than this, we have the OCRS value. The OCRS value, if we want a specific value, we should return to this equation to give us the value of the OCRS if the duty percentage were given, and of course the BR will be given. Actually, we just got it 3,190 something. Sorry, it's 3,124. But in this example, we will start with OCRS equal to 0, and then we will increase it or decrease it based on the switch that we are going to press, whether it is the increment or the decrement switch. So we make it initially equal to 0. Now for this one here, this is actually is very important statement that configure or sets the output compare 1 a remappable output. So now we know the output compare 1 doesn't have a bin associated to it. So we need to use RP14. In this case, we used RP14. We could use any of the RPs. We have so many of them. You can go back to the bin diagram that we discussed in the last lecture. So here we choose RP14, and to assign the output compare 1 for RP14, you assign it this way. You would say underscore RP14 register, which is this one, our choice, is equal to 18. 18 is actually the code for the output compare 1. And we will see this code with all of the other codes for other modules when we talk about the interrupts later. Part of the interrupts, we need some assignment using the RPs, and we will talk about all of them later. But currently, we just remember that for output compare 1, the code for it is 80. Once you configure everything, here, you start the timer. Now, if you start the timer, the output compare will be generated, start generating. Now, actually setting up the output compare control register was super easy. This table is actually telling you how did we set it up. We chose the OCM 011, and the output compare timer selector is 0 since we choose timer 2. The value of the OCRS, it could be anything because we have 2 switch to increment them and decrement them. And this is the main code. You call the method that we just had, configure output compare, and then you configure both switches, the decrement switch and the increment switch. And we go through while one, which is a forever while. If the increment switch is pressed and released, then you need to increment the value of the OCRS to increase the intensity of the light. If the decrement switch is pressed and released, then you need to decrement the value of the OCRS to reduce the intensity of the LED. Now, the if statement here to make sure that you don't exceed the limits. So for the increments switch, make sure that the value of the OCRS is still below the PR2. So it's still below this. If they are equal, you can't increase the RS to exceed the PR2. Similarly, for the decrement of if the OCRS is more than 0, you can decrement. If it is 0, then you can't have a value less than 0 or a negative value. And that's why we have these if statements. Now let's have another application for the output compare, which is the DC motor speed control. So what happens here, you have a big 24, and right now we know how to program our microcontroller to send an output compare signal based on our specification. Now what happens here is this will be, if you want to connect it to a DC motor, the one that you can see here, you can, the DC motor is actually change the electrical energy to a mechanical energy where you can move the, if you put, for example, the toy tire here, it could move clockwise or anti-clockwise based on the setup of the DC motor. Now the output compare we already did. Now the relation between the high time or the OCRS or the value of the duty percentage is going in proportion with the speed of the DC motor. So the more high time you have, the more speed you will have in the DC motor. Now, what about the direction? Going forward or backward? It's based on this connection that you see here. Notice that we have two elements here. This is a snubber or a protection diode, and it sets your direction and also limits the voltage spike. And here we have a transistor. This is an NMOS transistor, and the NMOS here, if you have the value equal to 0 at the gate, it will behave like a switch and it will be completely off. If it is 1, then it will be on. So there will be connection between the ground and this line. And you can see that in the top here, we have a VDD. So there will be voltage difference across the DC motor, and the DC motor can run. Now, to understand this better, let's see the first setup. If we have these switches in this direction, now we know the direction of the current goes this way. So it will move through this red line, and it will go across the DC motor in this direction. This will be translated to the anti-clockwise rotation of the DC motor. Now, if you have it the other way around, if you change these switches to the other option, it will be like this. And now this current still the same direction, but it will go this way, and it will be through the DC motor in the other way, and it will go back and so on. So this will be the clockwise direction or the clockwise rotation of the DC motor. Now, instead of having to connect all of these connections through the DC motor, one way to make it easier is to have this driver. It's called quad half-bridge driver. This is its name. It's from Texas Instruments, another company that supplies chip. And you can see here that you should generate 2 signals from the big 24. We have the output compare, the one that we have. You also need RB X and RBY. It could be any bits of port B or A. So you connect one here, one for 2A and one for 1A for this chip. It also has two voltage. One voltage is 4.5 or 5.5 voltage to supply the logic. And we have here the VCC2 4.5 all the way to 36 voltage, because we don't know what will happen to the DC motor. Do we have a very simple DC motor, a bigger DC motor for maybe big gates, maybe your car garage, if it has a roller or any kind of an automatic door that opens automatically and closes automatically, it must have a DC motor. And that DC motor needs a higher voltage. If you're talking about a toy, maybe 4.5 volts, maybe even less is enough. And now the way this quad half-edge driver operates is mentioned here in this table. If the enable is 0, these two values will be don't care, and the direction will be, as you can see here, cost. Now, if you have the enable equal to 1, now if you put 0 and 1 here in 1A and 2A, if you put 1, 0, then the direction will be forward. If it is 0 and 1, it will be reverse. If it is 1 and 1, then you will break or start stopping the DC motor. That's what this driver can do for you. It makes things easier for you. You just need to do this connections. This will be a simple interface. You have 3 lines connection between the big 24 or the microcontroller and this driver, and then you have only 2 outputs here. You will supply to the DC motor plus and minus, and you're done with the interface. So it's fairly simple. If you look here, there's so many things that you need to worry about. It's actually called half bridge driver, as you can see in the title. Now we'll have one more example. In this example, we say that a big 24 processor is driving a DC motor using a pulse width modulation output signal. And here are the requirements. You have the OSC 10 meg. The PWM is 1K hertz. The OC1 will be mapped to RP10. So now we map it to another RP. The DC motor has a maximum speed of 500 rounds per minute when the PWM duty cycle is a 100%. So 500 rounds per minute means 100% duty cycle. Now, this problem needs a C function for setting a PWM with a buff requirement and adjust the duty cycle with the given input speed. And the speed is in range from 0 to 500. This is the maximum, this is the minimum. And the function header will look like this. You set the PWM and you give it to the speed as an argument of this type. So to do this, first, we need to set up the timer. Next, we need to know what is the value of the OCRS. In the previous example, the OCRS was just 0 and the switch take care of everything. Here, we don't have switches. So we need to worry about the OCRS here. How to have, or what's the relation between the speed of the DC motor and the OCRS. So to solve this question, this is their timer equation. This is the FCY, it's 5 megahertz, since we have the value 10 megahertz, so it's 5 megahertz here. The PWM period is 1 over 1K, so it's 1 millisecond. That's the period. And now we try the prescaler 1, 8, 64, and 256, but luckily one works. So we stopped right there. We have PR2 equal to 1 millisecond, which is this 1 millisecond for the PWM period, times 5 meg, this is the frequency, the FCY, divided by the prescaler value, which is 1 minus 1, and it gives you the value that is between the 0 and the maximum capacity of the PR2 register. So it's that. So we chose this value. Now I know timer to control register is going to be 0x0000 because this one here, or this hexadecimal digit, is associated with the prescale value. So we're done with the timer configuration. For the duty percentage, and again, we can set it also in the table, the timer to control, the TCS and the T-gate is going to be 00, and the prescaler is 00. The PR2 is 4,999, which is this value. We fill it in the table, we're done. For the output compare, now to do the output compare, we know this relation between the duty percentage and the OCRS. We already discussed it. Now, what will happen is we say that for the maximum value, we would say that the maximum I know it's 500 round per minute. That's the maximum speed of the DC motor. We would consider 500 round per minute is the same as 100% duty percent. And from that, I will change the value of the I will change now this equation here, and I will make it this way. So if the maximum of the duty percentage 100, then the maximum of the speed in round per minute will be 500. This is the equalization that we had here. So anything less than that, we can find by adjusting the value of the OC1RS. So let's have OC1RS in one side and the other on the other side. So it will be like this. So now, whatever speed you have or you are given, the one that we said here in the argument, in this method, you will plug it in here, and then you will multiply it by PR2, the one value that we just found, the 4,999 plus 1, so it becomes 5,000 divided by 500. Now we can simplify this. This one, we already find it. It's 5,000 divided by 500. So you can find out that the end result here is that OC1RS is going to be equal to this speed times 10, which becomes very simple. Now, in the question, if you go back here, I don't think I identify the timer. Should you use timer 2 or timer 3? Since there is no specification, we chose timer 2 to be used for the output compare 1. And the selector, because of this, the OC timer selector is going to be 0, and the OCM, of course, it's 0, 1, 1. And this is what we have here. And now we are ready to write our code. This method would be like this. This is the timer 2 control register. This is the PR2. This is the timer 2, the beginning, it's 0. Even if you didn't write this one, is fine, since by default it will start from 0. Now the underscore RB10 register will be associated with the code of the output compare. This way, the output compare 1 will be associated with RB10. The output compare control register is equal to 6. And the OCRS now is equal to the speed multiplied by 10 from the calculation that I just explained to you. And after we're done, we start the timer. And now this method is complete. It sets the pulse width modulation based on whatever speed you want. Now, this problem didn't ask what will happen in the main method, but if you want a certain speed in the main method, you would just call this function. So in the main, you would say, okay, I will call this one, and I will simply say set PWM, and then I will give it the value that I want. If I want the speed to be 2, so the OCRS is going to be speed multiplied by 10. It will have value of 20, and so on. It depends on the speed. So maybe you want the DC motor runs the at a constant speed, or you want to increment it every once in a while using a while loop or a for loop. It's based on whatever you like if you want a certain application. With that, we're done with the output compare. So this lecture, we covered the timer and the output compare. Next lecture, we will talk about the configuration bits and also the oscillator. Actually, the configuration bits and the oscillator should be the first module right after the CPU and the memory discussion that we had before. But I think it's better for everyone that we discuss the GPI, which is a simpler module. Also, the timer and the output compare, they are fairly easy. And then we can talk about the configuration bits that you need to set up before you work with the microcontroller. So you need to set up so many things. So because of that, I thought maybe we push it a little bit later, and this is what we will discuss next time. So I'll see you next time with the configuration bits and the oscillator.